Okay, welcome to number 6. This should be the last one for the year, and this one's actually got 2 topics in it, and they're both fairly short, although one of them will need some expansion in class. The first one's about light sources. This seems like a strange little add-on that I think is extremely unlikely to get examined, but one never knows. So an incandescent light globe is an old-fashioned light globe. The old hot ones, some of them do still exist, and very roughly they peak at around that level and tail off again. So they have a range of frequencies. A coloured LED. Can be made to produce a very narrow frequency range. Laser. A single frequency in phase polarized. In phase means all of the waves are stepping at the same time, so all of the peaks are together, all the troughs are together. Okay, the last one we need to know a little bit about is light from the synchrotron. Due to the high energies involved, the light released from electron collisions is extremely bright. Highly polarized. Do it again with polarized. Very short pulses. And a broad range of frequencies. Okay, I'll put that up on the screen a little bit better than on Angie. Then we'll turn over and we'll finish off. So leave that there for a second or two, and then we'll move over. And we'll do the second half of the final topic. This will be about Heisenberg. Heisenberg's uncertainty principle. The smaller the measurement, the more the uncertainty in the results. of measurement at an atomic level causes a change in the result. So let's put it for another perspective. The more exactly the position of a subatomic particle is known, the less is known about its momentum. And the reverse also applies. Make sure you've watched the background videos because there's more detail. So if we take the delta x to be position, delta p to be the momentum, they've always got to be larger than a very, very small number, so equal to or larger. So therefore it doesn't apply to large objects, or does not affect large objects. It only affects really tiny things. Now it also applies with the energy. Haven't seen any questions that actually bring up the energy yet though. So, energy, time. So what we're saying is that the when is also variable when it comes to subatomic particles. Let's just finish off with single slit diffraction. Oops, two A's in diffraction, that really doesn't work. Okay, with single slit diffraction, even occurs with one photon at a time. The variation occurs due to the uncertainty principle. What this means in a very crude version is, if you've got the electrons and you've got a stream of electrons and they come to a gap, and the gap has to be really, really small for electron diffraction. So because you've made the gap very, very small, you've decreased the variation in position. So very small gap. So you've decreased the uncertainty of x, the position. So what this does, it increases momentum variation in the opposite plane, so in the plane shown, and I'll put that on the diagram. So it means that it increases the variation. So momentum variation increases this way. Okay, so sorry, some of that wasn't on the screen. I'll put it on the screen, leave it there for a while. So we'll reiterate, the electrons are coming along in a nice happy stream. They hit a very small gap. Because the gap is very small, therefore we've controlled the variation in x, and because of that it increases the momentum variation up and down according to this diagram, and so the photons actually spread out, so the electrons spread out much more than you would expect. You would expect electrons to go straight through in a straight stream, but they don't. They spread out just like light and actually create a diffraction pattern. Right. We are finished. Number 6 for this topic. I'm sure there will be small bits of the entire course that we've missed, but we'll tidy those up during the revision process. So good luck with the last couple, and make sure again that you have watched the background videos.